However, for trilateration to yield accurate results, the system must also account for the curvature of the Earth. The Earth is not a perfect sphere but an oblate spheroid, meaning it is slightly flattened at the poles and bulging at the equator. This shape can introduce complexities when calculating distances and angles, particularly at larger scales. Engineers have to incorporate this curvature into the mathematical models used in GPS algorithms to ensure that the calculated distances align with the actual surface of the Earth. Moreover, as the number of satellites in view increases, the position accuracy improves significantly, illustrating the importance of having a well-distributed constellation of satellites. This redundancy not only enhances the reliability of the system but also allows for error detection and correction processes, where the receiver can identify inconsistencies in the signals received from the satellites. Additionally, the concept of pseudoranging is crucial in understanding how trilateration works within the GPS framework. Each satellite continuously transmits signals that contain a timestamp indicating when the signal was sent. The GPS receiver captures this signal and compares the time it was transmitted with the time it was received. This time difference is multiplied by the speed of light to calculate the distance to the satellite. However, since the signals take time to propagate through the atmosphere, the distances measured are technically pseudoranges rather than true distances. Engineers address this challenge by employing advanced techniques, such as employing multiple signal frequencies and sophisticated algorithms, to refine the measurements and minimize the effects of atmospheric interference, such as ionospheric and tropospheric delays. These adjustments are vital because even minor inaccuracies can lead to significant errors in positioning, especially given the vast distances involved. The influence of signal interference and environmental factors on GPS accuracy is another area where engineering and physics converge. Urban canyons, dense forests, and mountainous regions can obstruct satellite signals, leading to reflections, refractions, and multipath errors. These phenomena can complicate the signals received by the GPS receiver, which relies on line-of-sight communication with the satellites. To mitigate these challenges, engineers have developed techniques such as signal processing algorithms that analyze the incoming signals to differentiate between direct and reflected signals. Advanced filtering methods, like Kalman filtering, are employed to dynamically adjust and predict the position based on the latest available data, allowing the system to maintain accuracy even in less than ideal conditions. Moreover, the role of time synchronization in GPS cannot be overstated. Accurate timekeeping is the cornerstone of the entire system, as the calculations hinge on the precise measurement of the time it takes for signals to travel from satellites to receivers. Each satellite is equipped with atomic clocks that are calibrated to maintain a precision of better than a billionth of a second. This level of precision is essential because a mere 1 second error can lead to positional inaccuracies of nearly 300,000 kilometers, given the speed of light. Engineers have developed synchronization techniques that ensure that all the atomic clocks are aligned and corrected for relativistic effects, allowing the system to function seamlessly across the vast distances involved. This intricate network of timekeeping ensures that the GPS operates with the reliability and accuracy required for a multitude of applications. As we continue to advance in both engineering and physics, the GPS system is likely to evolve further, incorporating new technologies and methodologies. For instance, the integration of GPS with other global navigation satellite systems, GNSS, such as Galileo and GLONASS, will enhance positional accuracy and availability. Future GPS systems may also leverage quantum technologies, which could potentially revolutionize the precision of satellite navigation. Quantum clocks, for example, promise unprecedented levels of timekeeping accuracy, further minimizing errors associated with relativity and signal propagation delays. As we delve deeper into the intricacies of GPS technology, it becomes increasingly clear that its success is a testament to the synergy of engineering and physics, showcasing how complex scientific principles can be harnessed to create systems that profoundly impact our daily lives. However, there are several challenges associated with this process. One key factor is the phenomenon of signal propagation. As the GPS signals travel through the atmosphere, they can be affected by factors such as ionospheric and tropospheric delays, which can introduce errors in the calculated distances. To mitigate these errors, advanced engineering techniques, including differential GPS, DGPS, and augmentation systems like the Wide Area Augmentation System, WAAS, are employed. These systems use ground-based reference stations to provide corrections to the GPS signals, enhancing accuracy. The phenomenon of signal propagation poses significant challenges to the accuracy of GPS systems. As GPS signals traverse the Earth's atmosphere, they encounter various layers that can alter their path and speed. The troposphere, which is the lowest layer of the atmosphere, is characterized by temperature, humidity, and pressure variations that can slow down GPS signals. These variations create delays in the signals, which in turn can result in errors in distance calculations. The ionosphere, a region of the atmosphere ionized by solar radiation, further complicates matters. The ionosphere contains free electrons that can refract and delay GPS signals, causing additional inaccuracies. To counteract these effects, engineers have developed sophisticated models that predict these delays based on real-time atmospheric conditions. For instance, the Klobuchar model is widely used to estimate the ionospheric delays, enabling corrections that help ensure more accurate positioning. To address the challenges posed by atmospheric delays, advanced engineering techniques have been integrated into the GPS architecture. Differential GPS, DGPS, is one such technique that leverages ground-based reference stations to enhance positioning accuracy. These reference stations are strategically placed at known locations, allowing them to calculate the discrepancies between their precise positions and the positions derived from GPS signals. The data from these stations is then broadcasted to nearby GPS receivers, which apply the corrections to their own calculated positions. This method significantly reduces errors caused by atmospheric conditions, improving the accuracy of GPS readings from meters to centimeters. The engineering behind DGPS involves real-time data processing. The algorithms must quickly analyze the discrepancies and disseminate corrections to multiple receivers simultaneously, showcasing the intersection of signal processing and geographic data management. Another prominent augmentation system is the Wide Area Augmentation System, WAAS, which serves to enhance GPS accuracy, particularly for aviation applications. WAAS utilizes a network of ground reference stations that monitor GPS satellite signals for discrepancies caused by atmospheric conditions. These stations continuously calculate the necessary corrections and relay this information to geostationary satellites, which then broadcast the corrected signals back to GPS receivers. The engineering challenge here lies in ensuring that the corrections are communicated effectively and efficiently, as the data must be transmitted with minimal latency to maintain the precision required for critical applications like aviation navigation. The algorithms employed in WAAS not only handle the real-time processing of atmospheric data but also ensure the reliability and integrity of the signals, which is paramount in safety-critical environments. Moreover, the incorporation of real-time kinematic (RTK) positioning is an advancement that takes the concept of DGPS further by allowing for even more precise localization. RTK positioning utilizes carrier phase measurements of GPS signals, which are significantly more precise than the traditional pseudo-range measurements typically used in standard GPS calculations. This method involves the use of a base station and a rover, where the base station receives signals from satellites and calculates its own position with high accuracy. It then transmits the corrections to the rover, which is usually within a few kilometers of the base station. The engineering behind RTK positioning requires highly sensitive receivers and sophisticated algorithms capable of processing carrier phase data. This technique has transformed applications in fields such as surveying, agriculture, and autonomous vehicles, where millimeter-level accuracy is essential. As we consider the challenges posed by atmospheric effects on GPS, we must also recognize the potential for future advancements in both engineering and physics to enhance the system's resilience. For instance, the integration of machine learning algorithms could lead to more adaptive models that predict atmospheric conditions in real time, enhancing the accuracy of the corrections provided to GPS receivers. By leveraging vast data sets from weather stations and satellite observations, these algorithms could dynamically adjust for delays based on current conditions, potentially mitigating errors before they impact navigation. In addition, researchers are exploring the use of new signal frequencies to improve the robustness of GPS. Currently, GPS primarily utilizes the L1 and L2 frequencies, which are susceptible to interference and atmospheric delays. By incorporating additional frequencies such as L5, which is specifically designed for safety-critical applications, the system can achieve improved accuracy and reliability. These newer signals are less affected by atmospheric conditions and offer enhanced resistance to jamming and multipath effects, where signals bounce off surfaces before reaching the receiver. The engineering challenges associated with these advancements include the need for new receiver technologies capable of processing multiple frequencies simultaneously, as well as the development of ground-based augmentation systems that can seamlessly integrate with the existing GPS infrastructure. While GPS technology has revolutionized navigation, the complexities of signal propagation through the atmosphere present significant challenges that require advanced engineering solutions and a deep understanding of physics. Through the integration of techniques such as DGPS, WAS, and RTK positioning, engineers have made remarkable strides in improving the accuracy and reliability of GPS systems. As we continue to innovate and explore new frontiers in both engineering and physics, the potential for even greater advancements in GPS technology remains vast, promising a future where our ability to navigate and understand our world is enhanced beyond current capabilities. Another significant aspect is the effects of relativity, which brings us to a fascinating intersection of physics and engineering. According to Einstein's theory of relativity, time can pass at different rates depending on relative motion and gravitational fields. GPS satellites are in motion relative to the Earth's surface and are also farther away from the Earth's gravitational pull. This results in two effects: time dilation due to relative velocity and gravitational time dilation due to the difference in gravitational fields. The effects of relativity play a crucial role in the functioning of the global positioning system, illustrating a remarkable intersection between physics and engineering. At its core, Einstein's theory of relativity proposes that time is not a constant but can vary based on the relative motion of observers and the gravitational field in which they exist. In the context of GPS, this theory is paramount because the satellites orbiting the Earth are not only moving at high velocity, so approximately 14,000 kilometers per hour, about 8,700 miles per hour, but are also located in a gravitational environment that differs significantly from that experienced on the Earth's surface. This duality of effects introduces complexities that engineers must account for in the design and operation of GPS technology. When considering the concept of time dilation due to relative velocity, we delve into the fundamental principles of special relativity. As the GPS satellites travel at speeds close to that of light, time for these satellites actually moves slower relative to observers on the Earth. This phenomenon is known as time dilation, where the faster an object moves, the more pronounced the effect becomes. For GPS satellites, this translates to their onboard atomic clocks ticking slightly slower than those on Earth, which, if uncorrected, would lead to discrepancies in positioning information. Engineers, recognizing the potential for substantial errors on the order of about 7 microseconds per dia, have ingeniously incorporated relativistic corrections into the GPS software and satellite design. By calculating these effects ahead of time, they ensure that the satellites remain synchronized with ground-based systems, maintaining the integrity and accuracy of the entire navigation network. In addition to time dilation due to relative motion, gravitational time dilation presents another layer of complexity. According to general relativity, time passes more slowly in stronger gravitational fields. Since GPS satellites orbit at an altitude of around 20,200 kilometers, they are in a weaker gravitational field compared to clocks on the surface of the Earth. This gravitational difference causes the atomic clocks on the satellites to tick faster than those on Earth by approximately 45 microseconds per day. When you combine this faster ticking with the slower ticking caused by their speed, the net effect is an overall gain of about 38 microseconds per day for the satellites. If engineers did not adjust for this discrepancy, GPS readings would drift by approximately 10 kilometers per day, rendering the system ineffective for precise navigation. The interplay of these relativistic effects highlights the remarkable ingenuity of engineering solutions devised to mitigate potential issues. GPS systems utilize precise atomic clocks that maintain accuracy to within a billionth of a second. These clocks are meticulously calibrated before being launched into orbit, taking into account both types of time dilation. Engineers have developed complex algorithms that run in the background, constantly adjusting the time signals transmitted by the satellites to compensate for these relativistic effects. This level of sophistication ensures that even when satellites are hundreds of kilometers away, their signals remain synchronized with those of terrestrial receivers, ultimately enabling precise location determination across the globe. Moreover, the engineering challenges do not end with the initial calculations. The environment in which these satellites operate introduces additional complexities. Factors such as the Earth's atmosphere can alter the speed of the GPS signals, which travel at the speed of light but can experience delays as they pass through varying atmospheric densities and temperatures. Engineers have implemented sophisticated models that account for these atmospheric effects, ensuring that the GPS system remains reliable under a range of conditions. The ongoing research into improving these models is a testament to the dynamic nature of engineering in the field of navigation technology. As we look to the future, the continued advancement of GPS technology promises to further enhance our understanding of relativity and its practical applications. The introduction of new satellites equipped with improved atomic clocks and more robust signal processing capabilities will lead to even more precise positioning. Additionally, the integration of GPS with other global navigation satellite systems, GNSS, opens up new avenues for collaboration, where cross-validation of signals can mitigate errors and improve accuracy. Engineers are also exploring the possibilities offered by emerging technologies, such as quantum computing and advanced machine learning algorithms, which may one day allow for real-time adjustments to signals based on a wide array of data inputs. The relationship between engineering and the physics of relativity within the context of GPS is a vivid demonstration of how theoretical principles can be applied to solve practical challenges. The intricate dance of time dilation, whether due to relative motion or gravitational effects, requires a sophisticated engineering approach to maintain the functionality of GPS technology. This remarkable interplay not only allows us to navigate the Earth with incredible precision but also deepens our understanding of the fundamental laws governing our universe. As we advance into a future shaped by these technologies, The legacy of GPS will undoubtedly continue to inspire innovations that bridge the gap between theoretical physics and real-world applications. In essence, the atomic clocks in the satellites tick slightly faster than those on Earth. Without accounting for these relativistic effects, GPS would accumulate errors of several kilometers each day, rendering the system unreliable. Engineers have implemented corrections for these relativistic effects in the GPS software, ensuring that the time measurements remain synchronized between satellites and receivers. The intricate relationship between time and relativity plays a pivotal role in the functionality of GPS, particularly concerning the atomic clocks on board the satellites. To appreciate the significance of these clocks, one must understand the principles of time measurement at high altitudes and velocities. At approximately 20,200 kilometers above the Earth's surface, where GPS satellites orbit, the gravitational field is weaker than it is at sea level. This difference causes the atomic clocks in these satellites to experience a phenomenon known as gravitational time dilation, which stems from Einstein's general theory of relativity. Essentially, the atomic clocks on the satellites tick faster than those located on Earth because they are less affected by the curvature of space-time created by Earth's mass. This seemingly slight discrepancy is crucial without precise synchronization between satellite and ground-based clocks. The timing inaccuracies would escalate rapidly, leading to substantial errors in positioning calculations. For instance, if the clocks were left uncorrected, they could drift apart by as much as 38 microseconds per day, which translates into an error of nearly 10 kilometers in calculated position, rendering GPS unusable for practical navigation purposes. The engineering challenge lies not only in recognizing these relativistic effects but also in devising robust methods to counteract them. GPS engineers have meticulously integrated relativistic corrections into the system's architecture. These corrections are encoded in the satellite software and are routinely updated to ensure ongoing synchronization between the satellite clocks and ground-based receivers. The system is designed to apply these adjustments automatically, allowing for seamless operation without user intervention. Each satellite broadcasts its position and the precise time the signal was sent, and the receivers are programmed to apply corrections based on predetermined algorithms that account for both special and general relativity. This integration of physics into the engineering design of the GPS system exemplifies a harmonious relationship between theoretical concepts and practical applications, showcasing the beauty of how scientific principles can directly influence technology. Furthermore, the significance of atomic clocks in GPS extends beyond mere synchronization. They are a testament to advancements in precision timekeeping technology. Atomic clocks operate on the principle of using the vibrations of atoms, typically cesium or rubidium, as a reference to measure time intervals. The accuracy of these clocks is paramount. They can maintain precision to within a few billionths of a second over long periods. Engineers continuously push the boundaries of this technology, exploring innovative designs such as optical lattice clocks, which utilize lasers to trap and cool atoms, allowing for even greater precision than traditional atomic clocks. As we look toward the future of GPS, such advancements could enhance the system's accuracy even further, reducing errors caused by relativistic effects and atmospheric delays. In addition to synchronization and precision, the integration of GPS technology into various fields showcases the importance of interdisciplinary engineering approaches. For example, in autonomous vehicles, GPS data must be combined with inputs from various sensors, including LiDAR and computer vision systems, to navigate safely and accurately. The engineering behind these autonomous systems must address the challenges posed by GPS signal loss in urban canyons or dense environments, where buildings can block satellite signals. By employing advanced algorithms and sensor fusion techniques, engineers can create systems that compensate for GPS inaccuracies, providing reliable navigation even in challenging conditions. The physics of light propagation, the mathematics of error correction, and the principles of control systems all come into play in developing these sophisticated technologies, highlighting the need for engineers to possess a broad understanding of various scientific disciplines. Ultimately, the ongoing evolution of GPS technology underscores the critical interplay between engineering and physics. As we advance into an era of increased reliance on precise location data, understanding the relativistic effects and developing new engineering solutions will remain paramount. Research into next-generation satellite systems, which might incorporate quantum technologies or improved signal processing techniques, holds the potential to redefine our navigational capabilities. Such advancements may lead to unprecedented accuracy in GPS, with implications for numerous applications, from emergency response and search and rescue operations to agriculture and environmental monitoring. The challenges ahead will require a concerted effort from scientists and engineers alike, working collaboratively to ensure that the legacy of GPS continues to thrive, empowering future generations to explore, innovate, and navigate the world with unparalleled precision. The ongoing evolution of GPS technology highlights a fascinating synergy between engineering and physics, fundamentally reshaping how we understand and interact with our environment. This relationship becomes increasingly critical as we find ourselves in an era where the demand for precise location data is escalating. The core principle of GPSA trilateration exemplifies how physics concepts manifest through engineering applications. As the global economy and daily life become more interconnected, the accuracy of GPS has ramifications that extend beyond simple navigation. It touches upon the very infrastructure of modern society. For instance, emergency response teams depend heavily on GPS to coordinate efforts efficiently during natural disasters, while agricultural sectors utilize precision GPS data to optimize crop management and reduce waste. Therefore, any advancements in GPS technology are not merely enhancements in convenience, they are foundational changes that support societal resilience and sustainability. Understanding the relativistic effects on GPS operations is another area where physics profoundly influences engineering practices. As we mentioned earlier, the atomic clocks in satellites experience time differently than those on Earth due to both their velocities and their position in a weaker gravitational field. This phenomenon not only necessitates complex engineering solutions but also requires an intricate understanding of Einstein's theories of relativity. Engineers must design systems that can effectively integrate these relativistic corrections into the algorithms that process location data. The implications of these corrections are far-reaching. For example, without accounting for relativity, errors in positioning could grow exponentially over time, causing inaccuracies that would be unacceptable in many critical applications. This interplay underscores the necessity for engineers to collaborate closely with physicists to ensure that the theoretical foundations are effectively translated into practical applications. Looking toward the future, the exploration of next-generation satellite systems holds immense potential for pushing the boundaries of GPS technology. Emerging concepts such as quantum positioning systems are beginning to gain traction, promising to revolutionize the field with unprecedented levels of accuracy. Quantum technologies, leveraging the principles of quantum entanglement and superposition, could potentially allow for measurements of position that exceed the limitations of classical GPS systems. For example, researchers are investigating the use of quantum sensors that could detect minute changes in gravitational fields, allowing for far greater precision in determining location. Integrating such technologies into satellite navigation systems could not only enhance accuracy but also significantly reduce vulnerabilities to jamming and spoofing, which are persistent challenges in current GPS applications. Moreover, Advancements in signal processing techniques are crucial for improving the reliability and resilience of GPS technology. The engineering challenge lies in developing algorithms that can filter out noise and enhance the clarity of signals transmitted from satellites to receivers. One promising avenue of research involves the use of artificial intelligence and machine learning to analyze vast data sets and improve the accuracy of signal interpretation. These technologies could help differentiate between genuine signals and those affected by interference, leading to faster and more reliable position fixes. As the landscape of GPS technology evolves, engineers must remain at the forefront of innovation, continuously refining their approaches to signal processing and developing new methodologies that harness the power of modern computational techniques. Environmental monitoring represents yet another critical application of advanced GPS technology. The precision afforded by enhanced GPS systems can facilitate real-time data collection and analysis in fields such as climate science, wildlife tracking, and natural resource management. For instance, scientists are utilizing high-accuracy GPS to study tectonic plate movements, providing insights into earthquake risks and informing construction practices in vulnerable areas. By integrating GPS data with geographical information systems, GIS, researchers can model complex environmental interactions and make informed decisions about conservation efforts. The synergy between engineering and physics in these contexts not only empowers researchers but also fosters a deeper understanding of our planet's dynamics, enabling us to respond more effectively to environmental challenges. The future of GPS technology is intricately tied to the ongoing collaboration between engineering and physics. As we explore new frontiers in navigational capabilities, it is essential to foster interdisciplinary approaches that unite scientists and engineers in their pursuit of innovation. By embracing the challenges posed by relativistic effects and harnessing emerging technologies, we can unlock a new era of precision navigation that holds transformative potential across multiple domains. The legacy of GPS is not merely about providing location data, it is about empowering future generations to explore, innovate, and navigate the complexities of the world with unparalleled accuracy and confidence. In doing so, we ensure that the technological marvels of today lay the groundwork for a brighter, more connected tomorrow. Moreover, the engineering behind GPS receivers is also quite sophisticated. Modern GPS receivers are designed with advanced algorithms that can interpret signals from multiple satellites simultaneously. This capability not only enhances accuracy but also allows for features such as real-time location tracking and navigation,